Our next talk will be given also a colleague from EIUB, University of Berlin from Switzerland, and Julian Rodriguez, talking about validation qualification of a space debris laser system at the Expert Center of Space Safety. Please.
Hello, everyone. So basically in this talk, we are just going to focus on the observable itself, and we will try to assess the different contributors to our observable so that we can use that for validate the stations. So to do that, I will start just stating the problem. We will have a short look at the observation equation. Then I will just provide an example. And finally, I would just like you to have the roadmap of the validation and qualification. So here we want three things. We want to assess the quality, the performance, but also the stability of a given space debris layer. Of a given space debris laser ranging system. So what we are gonna try to do is we're gonna build a model benefiting from your experience. So from the ILRS, from the previous studies that you conducted, and then we will try to compare observations against that model. So to do that, I would just like you to keep in mind this equation where we have the coordinates of the satellite, the coordinates of the station, the correction due to tropospheric effects, the system delays, the center of mass correction, relativistic effects if one has to consider them or not, the range biases and what could those range biases tell us, and then of course the error because we have a random process. So let's start with the satellite position. So here we wanted to have a figure of merit of how much can we rely on the different orbits that are available, for example, from the ILRS. So we took different analysis centers, so different orbits from the analysis centers, Lagius 1 orbits, 7 arc solutions, and we were comparing the overlaps. For those stations that, for those solutions or for the solutions provided by those analysis centers that there was no overlap, we were extrapolating the coordinates only if the error was smaller or equal to 5 centimeters. So we found that the orbits are in agreement of about 10 centimeters, and this is going to set up the baseline for our use of such predictions, of such solutions. So now the question is, okay, we have this reference, we know how those were estimated, but can we use predictions instead? So to do that, we just did the same exercise, and we compare predictions against the combined solution because, I mean, it's pretty obvious from the graph that is the most stable and it's the most representative because it combines all the ones provided by the different analysis centers. So we found out that, okay, more or less we can set up the baseline of 30 centimeters for what we can expect from the satellite position. Okay, now about station coordinates and eccentricities, we have two options. Either we estimate them within the framework of the ILRS, and you are all pretty familiar with that. So from that, what do we get? We get position, velocities, but also formal errors that we can use for assessing how good the coordinates are. And those are important to then really understand the impact when we are comparing these residuals, or when we are getting those residuals. And when we have the stations, I mean, as we saw through this week, it was also important to apply some corrections to those coordinates. For example, post-seismic deformation, tidal effects, and so on. But here I would like to bring back again these 30 centimeters that we are getting from the prediction. So it doesn't make sense to try to really correct for something that is smaller than that because you won't see the difference. So, but what if the sensor wants to be agnostic to any existing network? It's not a very good idea because it's the benefits I think that are obvious, or you can prove me wrong. So the question that arises when a sensor wants to be agnostic is what's the consistency with respect to the reference frame? Because we were using here orbits from Lagius 1, and this is those orbits that we are using are linked to a specific reference frame. So we need to find really the consistency between those. And how about the quality? Well, remember that we are only assessing single passes. So for those passes, we have to believe what you tell us about the quality of your own coordinates. Okay, so another important factor was the tropospheric delay that we have on our measurements, and here is just an example of a Legios pass that we observed in Zimmerwald. And you can see the order of magnitude and the dependence with respect to the elevation. But not only that, we also have dependencies with respect to the wavelength, and also we are dependent on the meteorological information that the station is providing to us. So we have at the moment we implemented two models to correct for this effect, and are the well known from the community. So the system delays, this is just to show an example from Zimmerwald, where we used a series of calibration measurements to derive the stability of the system. So we have measurements to our calibration, but we also know from an independent technique the geometrical distance. So if one removes that effect from the observed measurement to the calibration, then what remains are the system delays. And one is interested that those are stable in time. But we can also assess what is the spread, what is the dispersion of the single shot measurements. So this is what this plot is depicting. So this is very critical information, because if this is not stable enough, this will be directly mapped into the observable, and all information derived thereof. So that's very important. So center of mass correction, this is very critical, and I just want to highlight that this is only when we are using ILRS targets, because if the target is spinning, or you don't even know how big it is, or you don't have any information from where the return came, then it's a bit more challenging to judge that. But how should we proceed with new sensors? Here again, the value of the 30 centimeters that come from the predictions, and in the case of Legios 1, it's even smaller than that. So it should not play a significant role for at least at this stage, but it needs further investigation. And on that note, we can see here, for example, different other type of corrections that are important overall for geodetic applications, but that for us are not playing a significant role. For example, if we consider the correction for general relativity, we see that okay, we are at the centimeter level, and we were saying before that from the orbits we can get about 30 centimeters. So again, yeah, it's implemented, we do it, but will this play a role? I don't think so. So from on this slide, I'm just showing one example where we are only applying system delays from the raw measurements, and we see clearly the signature from the troposphere and the other error sources. And here, after removing all the errors that we quantified before. So here, what is important is, I don't know if you can really see it, but there are two things. First, it's not really centered in zero. That's suggesting a potential range bias, but also we can see the symmetry of the signature, and that might be related with a potential time bias. So how can we model for these two things? We go for a first order approximation. We just expand our observable integral series, and we estimate what we just said, the range bias and the time bias. And please don't be scared, overall the geodetic community, with these large values, because you are used to millimeters and microseconds. So it's just that we are assessing the station's coordinates and the satellite position as well. And this is really what is giving us this signature. The modeling that we are doing for correcting for these two effects is not able to really to make the residuals look flat. That means that accounting or depicting only the randomness of the measurements. So this is important. And this is what this plot is depicting. But then you will ask me, okay, this signature is not good, and you cannot use it for normal point formation. So then you can remove this signature if you apply just variations in the station coordinates or in the satellite position. So consistency check that we can do even if we have these orders of magnitude for the estimates of the range bias and the time bias is just, we use the same set of predictions, and then what we do is that we compute the time and the range biases per each pass from which we observe with the same predictions. This is very important. And as we can see, the consistency check, it's in good agreement, even though the magnitudes are a little bit higher, but it shows that the system is consistent. So shortly, I would just like to show you what's the roadmap for the validation and qualification. So we will have predictions, as we just saw before, that are good at up to the 30 centimeters in principle. Then we also have the characteristics from the station, and we have different levels for the measurement. So we have the filter full data, that is we have to detect, or we have to discriminate those good returns from the bad ones, and there are different methods to do that. Then you have the normal point formation, and it is also very well established. But here we can just use orbit determination and screen the residuals in the satellite fixed reference frame, for example. And in a second level, level 2, we will have consistency checks that we will use, as we saw before, to check how are those estimated time bias and range biases varying with respect to different passes observed using the same predictions. And finally, a level 3, that is the accuracy assessment, that if you have a reference orbit and you can use your measurements for estimating an orbit, then you can compare the two orbits and come up with a figure of merit that will describe the accuracy of your measurements. But not only that, it will also tell you how important it would be and how important your measurements are for generating orbits and benefiting from this observation technique. And on that note, I would like to thank you for your attention.
So thanks, Julian. We do have time for questions.
Thanks for that. I wonder, how can you tell between orbit error when you're flattening your residuals for these big space debris or whatever tumbling objects, and genuine changes in range due to the changes in attitude of the object?
Yes, that's a very good question. Here, the easiest way to answer that question would be that you can benefit from the knowledge that you have from an independent technique, for example, from passive optical, and then you derive how the object is moving, and then you know what to expect about this, and then you can use this information to really judge if what you are seeing on your signal or on your residuals comes from one thing or the other.
Okay, we don't have question from the line. Any other question? We have still time for a quick question. If not, I will thank our speaker and